All right, today we're doing 2.9 day 1, modeling with polynomial functions. So we're going to use finite differences to determine the degree of a polynomial function given a set of data. And we're also going to write a cubic function given some points. So first we're going to start with writing a cubic function whose graph passes through the points 1, 0, 3, 0, negative 2, 0, and 2, 1. So it's a cubic function and we see 3 zeros. So we're going to put it into interset form, but what we don't know is we don't know our a. So what we have so far is we have an a, our leading coefficient. We don't know what that is. And then for the 0, 1, 0, we're going to plug that in, x minus 1, 3, 0, x minus 3, and negative 2, 0, x plus 2. So since we don't know what a is, we have to solve for a, and luckily we were given another point, 2, 1. So we're going to plug that point in to solve for a. So 2 is our x, 1 is our y, so we'll plug those in. So 1 equals a times 2 minus 1 times 2 minus 3 times 2 plus 2. And simplifying that, this is 1, this is negative 1, and this is 4, which equals negative 4a. So then we divide by negative 4. So a is negative 1/4. And then we finish by writing our cubic function with an x and a y. So we plug in our a, and then x minus 1, x minus 3, and x plus 2. So this is our cubic function that goes through those zeros and that point. So we solve for a, and then we plug that back in. Next we're going to talk about finite differences. So this is used to determine whether y values for equally spaced x values, so going by the same amount, so in this case by 1, can be modeled by a polynomial function. So what we have to do is to determine the degree, we find constant non-zero numbers, okay? The first order differences, we find the difference between 3 and 1. So we always take the second one minus the first one. So 3 minus 1 is 2, 6 minus 3 is 3, 10 minus 6 is 4, 15 minus 10 is 5, and 21 minus 15 is 6. So all of those numbers are different. So I do not have constant order differences yet. So I'm going to find the difference between these. So 3 minus 2 is 1, this is 1, this is 1, this is 1. So this is our first order difference. This is our second order difference, and you notice that those are not 0, and they are constant. So that means that this can be a polynomial function, and it's going to be second degree. So our degree is going to be 2. If that doesn't happen, then it can't be a polynomial function. So this will always happen for polynomial function, and whatever degree that polynomial was is how many times you have to do the second order, third order differences. So that is the first example. Now we are going to show that the nth order differences from the given function of degree n are non-zero and constant. So this has a degree of 2. So that means when I have my table and I do my differences, I will get second order, constant second order differences. So we need a table of values. So you can find those values however you would like, but you can use a graphing calculator. So we'll do that here. So y equals x squared minus 3x plus 7. So you can graph that. You can see that's a quadratic Mine is not in the standard window, but we're going to go ahead and look at the table because that's what we're concerned with. And it doesn't matter where you start. I usually just go 1 to 6. You want to make sure you have enough in your table to see our constant differences. So I always do 1 through 6, but you can start wherever you want. So we're going to make our table. We have x and f of x. So we have 1, 2, 3, 4, 5, 6. And from our table, we see that this is 5, 5, 7, 11, 17, and 25. Okay, so now we are going to find our differences. So our first order differences, we take the second one minus the first one. So 5 minus 5 is 0. 7 minus 5 is 2. 11 minus 7 is 4. 17 minus 11 is 6. And 25 minus 17 is 8. So there's our first order differences. Now we are going to find our second order differences. 2 minus 0 is 2. 4 minus 2 is 2. 6 minus 4 is 2. And 8 minus 6 is 2. So this is our second order differences. And they are constant, non-zero. And this is a quadratic, so it is degree 2. So we have verified that that works for this polynomial as well. So if I have a table of values from a polynomial, this constant nth order differences is going to tell me what my degree of the polynomial is. And then I can, tomorrow we will find the actual function given a table. And we'll do one more. So again, you're going to type that into your calculator and you're going to look at the table. I'm just going to go ahead and put the table up here. You can make sure you can find that in your calculator. I'm again going to go from 1 to 6. And my y values are -4, 2, 34, 110, 248, and 466. At this point, I would stop the video and do this on your own, and then you can start the video and make sure you got the right thing. What you want to be careful of is this first negative here. You're going to do 2 minus -4, or what do I add to -4 to get to 2? So make sure you're careful with those negatives. So 2 minus -4 is 6, and then go ahead and stop the video so you can finish this and then check your work. So 34 minus 2, we get 32, 76, 138, and 218. We find the differences here. This is 26, 44, 62, 80. Find the differences here. 18, 18, 18. So these numbers are, this is my third, second, and first. So this is going to be degree 3, and we knew it was a cubic function. So we have verified that it has constant third order differences. And that is it. Tomorrow we will look at cubic regression and using a system of equations to actually find what the polynomial is given a table.